kernel PCA, we can just use the normal definition of PCA, but operate in this high-dimensional space. So I will, for starters, assume that the high-dimensional data has been centered. So after the implicit mapping to this high-dimensional space, then the covariance matrix is given by the outer product. So phi is the projection of my observation x to the high-dimensional space, and it's given by the outer product covariance matrix is given by the sum of the outer products across all observations. And so C is the covariance matrix. And then in PCA, we solve the following eigenvalue problem. So V is an eigenvector of the covariance matrix. And these solutions to this eigenequation all solutions V of this equation, they lie in the space spanned by the high-dimensional projections of our original observations. So where I goes from 1 to n. And because all solutions V are spanned by these high-dimensional projections, we can expand them accordingly. Okay, and we can now take this eigenequation and multiply it from the left. As follows. And we can then insert both this formula for the covariance matrix and insert this expansion here, and that will give us following. This time I think it's the battery that has, no, microphone is on. Yeah? No, but it says the battery is full. Even when I'm talking?
Better now.
Maybe it's just too low. So the battery says it's okay. All right. So Okay, now we can collect some of these to become kernels. So if I multiply with n, I obtain n lambda, and xi transpose xj is just the kernel. So the right-hand side I could rewrite as the kernel element or element ij of the Gram matrix. And that is the same thing as the Gram matrix times alpha. So on the right-hand side, I have n lambda k alpha. And here, similarly, the summation over k I interpret as a matrix product. So I could write this as and that, now going back to, so this is just the matrix product here. And so altogether what we're looking at here is the ith element of k alpha. And yeah, we have a single element on the left-hand side and a single, also only the ith element on the right-hand side. So I can summarize this as k, so the iterated application of k times alpha. Okay. Which is the same as that, or has the same eigenvectors as that. And so I have a new eigensystem here that I'm solving for kernel PCA. So if the data is centered in this high-dimensional space, then kernel PCA amounts to solving this. And if the data is not centered, then I need to use the doubly centered kernel instead. So if the data is not centered, then I should instead use C is now the centering matrix, not the covariance matrix. Now we diagonalize a doubly centered kernel matrix, and if you remember in MDS, we were diagonalizing. In MDS, we had the following. We were diagonalizing this thing here. So it looks very similar, and indeed it is the same thing for stationary and isotropic kernels. have that the kernel function between xi and xj is simply a function of the distance. And this can be normalized such that the similarity is 1 between the similarity between the point and itself is 1. And if we now look at the squared Euclidean distance between 2 points in a high-dimensional space, this can be multiplied out, so we would have this term we would have twice. And so this thing here is so the kernel that corresponds to f of 0, and f of 0 we had required to be 1. Okay, and this is just one element of matrix of squared Euclidean distances in this high-dimensional space. So the full matrix is then given by a scalar 2 times, these are again vectors, a vector all of 1s and a row vector all of 1s. And I can now multiply this with minus 1/2 and center doubly, as I do in MDS. So the factor of 2 disappears. And as we had seen an hour ago, this is just 0. So overall, what we have is that if we diagonalize this doubly centered kernel matrix, it's the same as solving the MDS problem. So in this was under the assumption that we made for stationary isotropic kernels. Kernel PCA amounts to a multidimensional scaling. That is performed on a dissimilarity matrix. which in turn is derived from the kernel that we use. So essentially what's written here is that distance is 1 minus the kernel, or 1 minus the similarity. Dissimilarity is 1 minus the similarity. So I have a picture here from the Smola and Schölkopf book. Which summarizes schematically what's happening in kernel PCA. Say these are the observations, and normally when we perform PCA, we find the first principal component, and then all points that lie along one of those dotted lines, they're projected to the same point on this first principal component. Now, in kernel PCA, we also do a PCA, but in the high-dimensional space, to which we implicitly map. So this picture is just the same as that. However, in the low-dimensional space, these lines that correspond to identical locations on the first principal component, in the low-dimensional space, these can become curved if this is a nonlinear mapping. The principal component itself is no longer possible to represent in this low-dimensional space. It need not have an image in this low-dimensional space. So that was schematic. Here's a toy example. Here is some data. And this is now for a polynomial kernel of degree 1, 2, 3, and 4. So polynomial kernel of degree 1 does nothing. In other words, this is just the normal PCA that we see here in the first column. And since it's just 2 dimensions, we can only get out 2 principal components. And the points which, or the set of points which maps to the same point on the first principal component is indicated by those lines. So in other words, my first principal component is this one, and my second principal component is that one. The third one doesn't exist. Now, if we take a polynomial kernel of degree 2, so we take a nonlinear mapping here, now these lines become curved. In other words, your first principal component would lie, if I did try to plot it, it would lie roughly here. And now I can obtain a first, second, and third score. And the advantage over conventional PCA is that if we have clustered data, can you please switch off the light at the blackboard? It's the very bottom left button, I think. Then the one next to it. Thank you. So we have 3 groups of data here. And what you see now is for the Gaussian kernel, for the RBF kernel, the first, second, third, fourth, fifth, sixth, seventh, and eighth scores on those eigenvectors or principal components. So the first principal component has large values for this cluster. It has 0 for that, and negative values for this cluster. So in other words, the first principal component does something like that. The first principal component visits all 3 clusters and is already sufficient to discriminate those 3 clusters. So here's a different representation in the scatter plot of the same data. So each point in this plot is a dot in this image here. And on the x-axis are the scores along the first principal component. And if we ignore the second PC, so if we project the data down, you will see that these points are the members of the first cluster. Then those points, they all project roughly to 0. You see they all lie in the same, or they have similar values along this first principal component. They all map to 0. And then those points here, they map to this cluster. So even the first principal component would be sufficient to visit all, or to discriminate all 3 clusters here. discriminate is perhaps not a good word because it's an unsupervised technique, but let's say to disaggregate or these three clusters. Then the second principal component is, of course, orthogonal to the first. So this one gives positive values to that cluster, negative values to the other. So this is the second principal component in the scatter plot. So you see these points are up here, and those points are down there. And then there are even higher ones. So this has been used sometimes, but the problem is that it does not afford, there's no easy way of plotting the principal components themselves. So kernel PCA, the thing to remember that kernel PCA, at least for stationary isotropic kernels, is just multidimensional scaling, where the dissimilarities have been obtained by the kernel that you choose for your kernel PCA. Okay, can we have some light, please? So we stick with diagonalization, but we're now going to really introduce graph structure on the manifold. And there are several methods that are very similar in spirit, but the first one that I want to show is Laplacian eigenmaps. And now we've entered the new millennium, so this is from Belkin and Niyogi, 2002. And the paper has Laplacian eigenmaps in the title. I will first give you the recipe, and then we look at the individual steps. So firstly, you need to construct the adjacency graph. So, in other words, if you have a number of points here, we could compute a dissimilarity between each point and every other one. But the idea, so if I plotted that as a graph, I would get all these crossing lines from connecting each point to every other. So in an adjacency graph, the distance, the idea is to connect only those points that are neighbors in some ill-defined sense. And your definition of neighbor, of course, determines the graph that you get out. But a nice graph, at least for 2 dimensions, would look something like that. So what I've drawn here is something like the Delaunay graph, but Delaunay graph, when you have noisy data in high dimensions, is very, it's not a sensible thing to compute. So what people do, and also because finding the exact Delaunay graph would be much too costly, so what people do instead here is to compute typically the epsilon nearest neighbor or the k nearest neighbor graph. So in epsilon nearest neighbors, you simply create an edge in your graph for each observation that, or for all observations that lie within the radius epsilon. In k nearest neighbor graph, you find the, for instance, 5 nearest neighbors and create an edge to those 5 nearest neighbors. In such nearest neighbors graphs, you need to distinguish between symmetric or asymmetric formulations. So, for example, if I do it asymmetric and I'm constructing the 1 nearest neighbor graph, then this point would be the closest neighbor for that one. That point would be the closest neighbor for this one. but this point would be the closest neighbor for that one. So here is a love which is not reciprocated. And you can build, you can parse these into undirected graphs if you wish. So however you do it, you need to construct an adjacency graph, and the idea is that that graph should be sparse on the one hand, so you don't want too many edges, but you also want it to be connected. So it doesn't help you if you have, you know, a lot of singleton clusters containing just one or a few nodes. So you want a sparse but connected graph. Then secondly, you need to choose edge weights. In this case, the authors have done the choice for you by arguing that the heat kernel would be a good idea to use. And in this domain of application, the Gaussian is sometimes called the heat kernel. So the weight for an edge ij is specified like that, where self edges are not allowed. So I could write that the diagonal elements of W should be 0, but I can also argue that this constraint is already implicit in the construction of the graph. So if I create an edge for each of the so-and-so many nearest neighbors, if I look for the 3 nearest neighbors of a point, I don't count the point itself, but I really look for the 3 neighbors, 3 neighbors that are closest by. And because of this step number 1, you could also say that this is a way of truncating your Gaussian kernel here. And then thirdly, you solve for the following, where so we've only talked about W so far, and L is given by W by D minus W, and D itself is the sum of all the edge weights that a given point has. So it's again a vector of ones performing the summation for us here. And L has a name of its own. This is the graph Laplacian. And it corresponds to the Laplacian operator, or the operator that computes curvature on a graph. So you solve this equation here, and you then find an embedding. By taking the first few eigenvectors that you have found here. So So when I write lowest eigenvectors, I mean the eigenvectors pertaining to the lowest eigenvalues. And it turns out that the first eigenvector is not usable, so you start with the second eigenvector and take the first p of them to obtain a p-dimensional embedding. So I'm going to use, again, the following convention, that this embedding y I will represent it in terms of a matrix, and this matrix should have p rows for my p dimensions and n columns for my n points. And when I write y1 or yn up to yn, these are the column vectors of y. So these all correspond to a given observation. Now, as the authors write, a reasonable criterion. So note that you know this is not a strict derivation, but it's something that you can motivate. For choosing a good map or a good embedding is the following, namely to find those vectors y that minimize the following expression. So in other words, so W is those edge weights, they express similarity. If you have a large weight, it means it's an important edge. And you want all points to be close to each other, but you especially want points with a large edge weight to be very close to each other. Now, as it stands, this has an optimum solution, which is given by all the y's being 0, which is not so, it's very low dimensional, but it's not very helpful. And this is why we will introduce some constraints in a minute. So subject to, let me write suitable constraints. That prevent a collapse onto a single point. So if I multiply this out, I will obtain a term where I have so the term which is quadratic in yi, and I obtain 2 of them because I also have this term which is quadratic in yj. And since this doesn't depend on j, I can pull in the summation over j, and that is just the definition of the ith element of my diagonal matrix D. And then there's the cross term. Okay, and I will now rewrite the same thing, but in matrix notation, or using indices into this matrix capital Y. So I have the outer summation over my different points, and this vector product I now really write explicitly in terms of the components. So the kth component of yi transposed is given by yki. Do the same thing here. So on the one hand, I really explicitly treat all the components in this inner product separately, but on the other hand, I use a capital Y to get to matrix notation. No, I would like to treat those two terms simultaneously, but the one on the right-hand side has one summation more. So on the right-hand side, I also have a summation over j. So to look these terms more similar, I will indeed do the following. I will exploit the fact that D is a diagonal matrix. So I can safely multiply also with these remaining non-diagonal elements of D. All right. Now, if I disregard the summation over k, this is just y d y transpose. And because I sum, you see I have this index k and that index k, so I sum only over the diagonal elements. So I should write that this will give me the trace in the end. And similarly here, I have minus the sum over k of y wy transpose. Or altogether, this is the trace, and now I can combine d minus y was my Laplacian L. So the reasonable criterion, subject to suitable conditions, is this one here. So I want to minimize, in a sense, the spread of y, where I weight the distances between observations by this graph Laplacian. So, but if I minimize that, the optimum solution will be a matrix of all 0, not very interesting. So we will introduce two constraints. On the one hand, I will require that y should have a given rank. But just this condition is not enough, because I might still make my y's arbitrarily small and make sure they have that they span a space of dimension p. So I should also say something about the scaling of these y's. And the condition I will use here is that the weighted spread of y along all dimensions should be 1. So the spread should reach a constant value, which I choose to be 1. And this is, so I is the identity matrix, and this is a p by p identity matrix here. And inserting this d here means that we compute a weighted spread where the weight of an observation depends on the number of edges with high weights that it has to other points. So it's a weighting matrix, and point I has a weight dii here. So if I now incorporate these constraints into the minimization problem, I'm left with the following. I want to find the optimum y such that this normalization condition I include by multiplying with its inverse. Such that the rank of y should be no less than p. And there's an equivalent formulation. One could also say that so this condition of having a minimum rank is already incorporated in this constraint here, because if y had a smaller rank, then I could not get this p-dimensional identity matrix here. And so this is something like a generalized